Hello, everyone, and welcome to Horizontal Tangents and the Definition of the Derivative. So I want you to consider the graph of a parabola. Many real-life things are represented by parabolas. The one that you probably are the most familiar with is a ball being thrown up in the air. So let's say you start at a height of 3 feet, you throw it up in the air, you know it's going to come back down. Now remember, this is not necessarily what the path of the parabola looks like. If you're a person standing there throwing it, you're probably going to, like I said, say from 3 feet, you're going to throw it straight up and it's going to come back down. This path represents over time what its height is. So this is a visual of time going by and it's getting higher and higher, and then time continues to go by and it goes back down again. There are times when you might want to find that maximum height. A parabola also represents the areas for various rectangles of a limited perimeter. So let's say you wanted your perimeter to only be 12. Well, then you could do a rectangle that was super long and skinny. 10. Oh, I was going to say, let's do actually a perimeter of 24. It'll give me more options. 24. 10, 10, 2, and 2. That would make 24. But that's really long and skinny. So maybe it would be better to make it a little shorter, like 8 and 8 and 4 and 4. Or maybe you want to make it pretty much a square. 6, 6, 6, 6. If you actually graphed all these different areas, it would look like a parabola, depending on how big you made the sides. And somebody might want to say, well, if this is the area and this is the length, if you know the length, you can figure out the width. And this is the length, you want to know what is the maximum area. How should you take what limited perimeter you have, maybe it's fencing or something, and maximize the area? Well, we've done these kinds of problems, and it's always been really easy. We've used negative b over 2a. The question is, what if you're studying something that is fifth power or fourth power or just something completely different? And this is where calculus is going to come in. When you were in Algebra 2 and pre-calculus, the only kind of max or min that you could find by hand was on a parabola using negative b over 2a. If you wanted to do a graph like this, then you had to use your calculator. Today, I'm going to tell you that this is what makes calculus students different from all the underlings in the other math classes, is that we can find those points by hand. What's special about those points? That's where the slope is equal to 0. So we've already learned that we can find the slope at different points. So now what we're going to do is we're going to find a formula for the slope, and then we're going to say, where is the slope equal to 0? And setting things equal to 0 is something you have been doing for a very long time. The name of these kinds of points are horizontal tangents. So you're still finding the slope of the tangent line, but where the slope has a horizontal tangent line. All maximums and minimums occur where the slope of the tangent line is equal to 0. And this truly is going to be the key to calculus. It's going to be the whole crux of what we do, including all of our word application problems. So I know I've been harping you on setting equal to 0 and factoring, but this is why. This is what's going to happen. Okay, so it says find the vertex of a parabola whose graph is formed by y is equal to x squared plus x. So this is not a problem that you need calculus for. If you factor this, you can graph it super quick. It has x-intercepts at 0 and negative 1. It's an upward parabola, so it goes like that. And honestly, because you know that the vertex is exactly halfway between those two, I can tell you that that point is going to have an x-coordinate of negative 1/2. And then to find the y-coordinate, all you have to do is plug it in. I didn't even need negative b over 2a. I cannot stress enough that throughout this year, if you have other math in your background that will allow you to get the answer to a problem, by all means, use it. However, I'm going to show you how we're going to do that using calculus on a nice, easy problem, so that then when we get to harder problems that you can't just look at it, or you can't just use negative b over 2a, you'll know how to do it. So the first thing is finding that formula. Every single problem requires you to find the formula for the equation for the tangent slope. So you need to find the formula for the slope at any point. I know that these videos have gotten to be very lengthy. I mean, if we were in class, I'd be teaching for an hour and a half. So even a 40-minute video, though, I know feels long. So I want you to stop the video. I want you to go ahead and do the problem all by yourself. Make your 2 points, make your a comma, a squared plus a, and then make your a plus h comma, a plus h squared plus a plus h. Do your limit as h goes to 0 and find the formula. When I collect your notes, I will be looking to see if you did this the long way. Okay, when you resume your video, you're going to find the formula came out to be 2x plus 1. If you didn't get that, then by all means, you should ask me and I'll do it with you. But that's the formula. Now, I don't want to keep writing, what is the formula for the slope at any point? So somebody knew that we were going to be spending the whole year finding this formula. So they gave it a notation so everybody would know that that's what you did. And that notation is y prime. That's how we pronounce that, y prime. And when you see that, that always means that this is the formula for the slope at any point. You can also use f prime. Why would you want to do that? For the same reason that we sometimes use f of x, because now I can plug a number in. This literally means the slope at x is equal to 1, because there's a little prime there, where this would mean the y value at x is equal to 1. I hope you see the difference. So we've used this notation for a long time. You know that f of 1 means the y value when x is equal to 1. Now I need you to know that this notation means the slope when x is equal to 1. And what is the slope at x is equal to 1? Well, let's just plug both of them in. For the y value, if you plug that in, 1 squared plus 1 is 2. So right here, 1 should be 2. I would say it came out pretty good on my graph. And what is the slope right there? I plug it into this formula. That is my slope formula. So 2 times 1 is 2 plus 1 is 3. So the slope is 3. Does that look like it could be a slope of 3? Yeah, I would say it does. So how does this apply to our lesson today? We're just going to add a step. You're going to take your formula that you just got, and the question is, where is the vertex? Well, the vertex is going to be where there's a horizontal tangent, where the slope is equal to 0. So if they ever want to know a vertex or any other max or min point, you can just say, all right, I'm going to figure out where this formula is equal to 0. Negative 1 is equal to 2x. X is equal to negative 1/2, which is what we already knew because we had looked at it and just known it. So it does say what is the vertex. Don't forget that that is an ordered pair. You are going to have to go back and find the y coordinate. Now, sometimes people get confused and they plug this into the wrong formula. Remember, this formula says y is equal to, it gives you the y value, which is what we want. This formula down here is the slope formula, and it'll give you the slope. I don't need that. I already know the slope is 0. I want the y value. So f of negative 1/2 is negative 1/2 squared, make sure you have your parentheses. If you don't use your parentheses and you type this into your calculator, you're going to get the wrong answer, is 1/4 minus 1/2, which is negative 1/4. Okay, mine does not look like negative 1/4. Honestly, mine looks more like negative 1. So it must be a little shallower than that, but that is the correct answer. Okay, we'll do another one. Find all the maximum and minimum points on the curve f of x is equal to x cubed minus 3x. I still would like you to graph it first. So f of x, factor out first. And then if you can, you would normally finish factoring because it has an x squared in it, but you can't. So you can stop there, but you should still be able to find the zeros. So the zeros are at x is equal to 0, and when x squared minus 3 is equal to 0, which is x squared is equal to 3, x is equal to plus or minus the square root of 3, which I would like you to memorize is approximately 1.7. So let's graph it real quick. It crosses through 0 and 1.7, negative 1.7. You know that it is a cubic function. You know that it's going to end up because it's positive. So I'm just going to sketch something. There we go. They want to know what that point is right there. The maximum and minimum points. Now I have to tell you, if I was going to take a guess, my graph tells me that the maximum is going to occur at -1 and the minimum is going to occur at +1. But I'm going to show you an easy way to do it using calculus instead of typing under your calculator, which is what you had to do in pre-calculus. So your first step is going to be to find the formula for the slope at any time. So f prime of x is the formula for the slope at any point x. Again, this is a long problem. I do not want to do it out on the video, but if you need help with it, by all means, that's what we can do during our Zoom class time, is talk about that. But I'll get you started. X and x cubed minus 3x is 1 point. Your second point would be x plus h. This is kind of a brutal problem. X plus h cubed minus 3 times x plus h. And then you would do the limit as h goes to 0 of y2, which is all of that, minus y1 over x2 minus x1. And that would give you your formula for your slope. I'll just tell you right now the answer, again, this work needs to be in your notes, is 3x squared minus 3. This is just such a cool formula. This formula says you ask me anywhere on the curve and I'll be able to tell you what the slope is. So f prime of 0 means the slope at 0. So if I plug a 0 in, I get -3. Does it look like the slope is -3 there? Totally. If I plug in a +3, I should get a steep number. So let's just try that. The slope at 3 is, going to be 3 times 3 squared minus 3. 9 times 3 is 27, minus 3 is 24. It is super steep. So at 3, it's really steep by that point. What do we want to know? We want to know where the slope is equal to 0. That's what makes a maximum and a minimum so interesting, is see the slope is negative and then it's 0. It flattens out just for a split second and then it shoots back up. I draw the whole tangent line so you can see it, but you're finding the slope at a little tiny point right there. The slope is 0 and then it starts to be negative. But most people draw it bigger. So they're drawing the whole line that is tangent to the curve at that point. So if you want to find, this is getting a little messy. If you want to find the maximum and minimum points on a curve, then you set f prime of x equal to 0 every time, the whole year. 3x squared minus 3. 3 is equal to 3x squared. X squared is equal to plus or, no, just 1 at this point. And then I was trying to hard to make sure I didn't forget, plus or minus 1. So there are two answers, which makes sense. There's 2 times when the slope is equal to 0. So at 1, now how do you find the y value? Whenever you want the y value, you need the y equation. Use the y equation. That's so important. So f of 1 is 1 cubed minus 3 times 1, which is negative 2. And that looks about right. At 1, it's negative 2. That's the min. Negative 1 is going to produce positive 2. And that's your max. I didn't actually do the workout. I know that you can do it. It's calculus. So there's your final answer. I found the minimum and the maximum, and you could not have done that any other way. Unlike a parabola, that if you get stuck and I give you a parabola, then just go ahead and use negative b over 2a, but that won't work in this case. Okay, so I keep saying over and over again this long phrase. The slope of the tangent line at any point is this formula. Yeah, that's really a mouthful. So somebody gave it a name, and that name is derivative. And this is a huge word because I'm just telling you right now, if you guys are at a family party and your grandmother comes up to you or your aunt comes up to you and says, oh, what are you taking in school? And you say calculus, they're going to say, oh, derivatives, right? Derivative is just the key word. It's the word that we're going to use all the way until the end of the year. And so it's the one thing that people remember about calculus. You can just nod politely and be like, yeah, derivatives, Aunt Sue, that's it. And that's fine. But hopefully you'll actually understand what it is. So the formal definition, this is not new. They are just reiterating what you've already learned. They'll say it 10 times in a calculus book. The derivative of a function is the function f prime of x. So like I said, this is the notation that we're going to be using, whose values at x is defined by, and then they give this new formula. And you might be thinking, what's up with that? It's the same formula as before. We learned it like this, f of x plus h minus f of x. The first time I saw this in a book, I thought, what is this formula? It's the same formula. They just chose to rewrite it with a new notation. It's the identical formula. Don't let it throw you. So instead of saying h, they said delta x both times. And like I said before, they've crossed off the x's to simplify it. But I really like when those are there because it helps you see that it's y2 minus y1 over x2 minus x1. So what they're saying is if you have a formula, if you have a curve and this is the point x f of x, then this is the point x plus a little change. Do you remember that delta means change? A little change in x. And then f of x plus delta x. Those are the 2 points that they've done. And then they're just saying, if you let that delta x, if you let that little change become 0, then you're pretty much the same point. So it's introduced much later, not just by me in my lessons. I do follow a normal calculus book so that you're ready for college. Because they want you to understand the concept with the limit and everything. But now they give you the formal definition. This will be a test question. The question will be, what is a derivative? It is the formula for the slope of the tangent line. Or some people say it's the formula for the slope at any point on a curve. That's great too. So there you have it. This is the key to calculus. That is the definition of a derivative. So I'm going to do two more derivatives today that we haven't done just because they're a little bit harder to do the limit for. These will be on your test. But, well, it won't be x minus 3. It might be x minus 5. But the concept of doing one with a square root, and you'll see that number 2 is a rational function, which we have done, but we're going to do another one because they're pretty hard. So again, find the derivative means we're going to find a formula, f prime of x. Our graph, this has been moved 3 to the right, 1, 1, 4, 2. It looks something like that. Okay. I'm going to make up 2 points. One of them is going to be x comma the square root of x minus 3. And my second point is going to be x plus h comma x plus h minus 3. This problem is lovely in that I didn't have to do anything to simplify this point, x plus h minus 3. But there is a little bit more of a learning curve in figuring out how to actually simplify this limit. So y2 minus y1, which is square root of x minus 3, and then x2 minus x1. As you guys know, the x's always cancel, which leaves me an h on the bottom, and that's why we need a limit, because you can't actually have h be 0. There's nothing short of this. I'm just going to tell you, this is a trick, and you have to learn it. I think it was on limits D for the homework. The way that we solve one of these is to multiply the numerator and the denominator by the conjugate, which is x plus h minus 3 plus, did I make that big enough? X minus 3, and then the same thing on the bottom. X plus h minus 3 plus, that's what a conjugate is, when the two terms are the same, but the thing in the middle is opposite. So if it was plus, it's minus. If it was minus, it's plus. On the top, I'm going to multiply that out. So the first times the first is going to give me x plus h minus 3. The inners and the outers cancel, which is the whole purpose behind using the conjugate. And then the last times the last, be careful here, the last times the last is x minus 3. But if you forget the parentheses, it's minus the whole thing, x minus 3. So you do have to be just a little careful there. I would not bother to multiply this out because you really are going to want to factor out the h anyway so you can cancel it. So don't bother to distribute the h. That gives me the limit as h approaches 0 of, just going to put this right up here. And then that gives me x minus x is gone, negative 3 plus 3 is gone, and I just have h over h times x plus h minus 3 plus x minus 3. And of course, what did that do for me? It got the h's to cancel. Not often, but every once in a while, somebody thinks that the numerator's gone. Be careful, the numerator's not gone. It is a 1 holding that spot. You do not need to show this step. I'm just taking my time because I know not everybody can write as fast as I can and be listening. So I'm going to show that step. But now that that h is gone, I can plug 0 in. Oh, so I don't need the limit anymore. I can actually plug 0 in. And when I put 0 in there, I get 1 over the square root of x minus 3, because that h is gone, it was 0, plus the square root of x minus 3. So if you have one square root of x minus 3, and you add to it another square root of x minus 3, you have 2 square roots of x minus 3. And that was a super long problem. What did we find? We found a formula for the slope at any point, but instead of having to say that big long phrase, now we can say we found the derivative. So the derivative is what we were finding. It's way down here. Always good to try a few points. F prime of, I would say at 3 what's happening, or at 4 what's happening. Notice you can't plug in a derivative at 2. You can't do it. You'll get a negative underneath the radical, which makes sense because there is no graph before 3, so there's no derivative before 3. But let's just do 4. So 1 over 2 times the square root of 4 minus 3 is equal to 1/2. So at 4, does the slope look like it could be 1/2? Sure. Okay, so you found the derivative. You found a formula that will tell you the slope wherever you want to know. As this number gets bigger, you should get a smaller number, right? This is flattening out. So the bigger you go, the flatter it should be. 1 over 2 square roots of 10 minus 3. I have no idea what that is, but it doesn't really matter. The bottom line is it's 1 over a number, so it's going to be pretty small. This is not required. I'm just always trying to make sure you understand what we're finding, because it is going to be the key to the rest of the year. A derivative is a formula for the slope at any point. All right, we're going to do one more rational function. The purpose of this is to practice your clearing fractions. If you would like to pause this video and skip ahead, by all means, you can do that. I am going to go through it a little fast because it's not the first time. But if you want to pause the video and see if you can do it on your own, the answer is -1 over x minus 5, the quantity squared. Okay. All right, for those of you that need to see it done, you know I want to start with a graph. There's an asymptote at 5, vertical asymptote. And then the other asymptote is right at 0 because the power of the numerator is less than the power of the denominator. And if I plug in 0, I get -1/5, which tells me the graph is there, which means the other graph is over, the other branch is over there. I'm going to pick my 2 points. I have x and 1 over x minus 5. I have x plus h and 1 over x plus h minus 5. And I'm going to do a slope between those 2 points. So I'm going to do y2 minus y1 all over x2 minus x1. And that would give me the slope. But because I actually want to find the slope at a specific point, at this red point, I really want h to be 0, which I know it can't be, otherwise they'd be the same point. So I'm going to take the limit as h approaches 0. The key to doing these problems is to get a common denominator. So this one needs an x minus 5 on the top and the bottom. You are required to show your work correctly. You're adding it to the top and the bottom. And this one, you're giving an x plus h minus 5 to the top and the bottom. The bottom doesn't need anything. Okay, when I actually distribute that, so now on the numerator here, I get an x minus 5. They're going to have the same denominator, so I'm going to go ahead and put them together. These 2 terms have the same denominator. Oops. So I'm going to go ahead and put them together. This numerator is now x minus 5, and this numerator is x plus h minus 5. But you're subtracting it. So it's actually going to be minus x minus h plus 5. Don't forget to rewrite your little limit in there. And don't forget, because it's a complex fraction, there's actually a whole denominator still. There's still an h there. We're going to tidy that up a little bit. So the x's cancel, the 5's cancel, and I get negative h over x minus 5 times x plus 5. Oops, sorry, x plus h minus 5 all over h. To do a complex fraction, you really want a whole fraction on top and a fraction on bottom. And then you can keep this one, change it from division to multiplication, and flip the second one. Keep, change, flip, or flip and multiply, which is what I do. Now my h's cancel. H divided by h is 1. It is easy for people to forget the negative. I'm always going to try and point out to you what people do wrong. Losing that negative and not distributing it up here are two places that people go wrong. But now I don't have a complex fraction anymore. And now that I don't have a complex fraction, I can plug in an h is 0. I don't have to rewrite the limit anymore because I've actually done it. And now that h is 0, I get this, which of course I would probably write as x minus 5, the quantity squared, which I had written the answer at the beginning for people that were skipping ahead. Don't forget to label it. This is the derivative, which is a formula for the slope at any time. And I got to just keep saying how interesting it is to look at it and know that it makes sense. Because the bottom is squared, the denominator is always positive. And because the numerator is negative 1, you are always going to have a negative divided by a positive, which is always going to be negative. And if you look at the graph, it's always negative. This one's pretty flat, but it's just ever so slightly negative. And it gets really negative. But then even over here, it still has a negative slope. The slope is never positive. So that should give you some assurance that that makes sense. And when f gets really, when x gets really big, let's say 100, way out here, look what happens. 100 minus 5, 95 squared, it's huge. So for all intents and purposes, its limit is going to be 0. And sure enough, its slope way out there is going to be 0. So hopefully you're getting a sense of how this all fits together. So these two derivatives are definitely going to be on your test. Make sure you can do ones with radicals and ones with rational functions, because they're different and they're a little hard. In addition, of course, to your basic polynomial function, x cubed minus 3x or something like that. All right, we have hang in there. We have 3 questions left for today. They're pretty short. As is true for limits, the left-hand derivative and the right-hand derivative must be the same in order for there to be the derivative at a point. And for derivatives, the function must be continuous. So let's just graph this super fast. Negative x, but not actually at 0, is a negative slope that's coming in like that. This is a parabola. Always factor it to graph it. It crosses at 0 and at 1, and it's going like that because it's an upward parabola. I get to fill in the dot because this is where it's equal to. So this is continuous because the two sections connected. The question is it differentiable? So here's a big word, differentiable. And what that means is, does the derivative as you're coming down here match the derivative here? So this derivative is really easy. It's a line. Its slope is -1 the entire way. So the question is the slope here also -1 right at that moment? Well, the only way to know that is to figure out the slope formula. You're not required to do this. I'm going to tell you the slope formula. By now, during Zoom, I've probably told you a shortcut for figuring it out, but I'm not going to do that here. So the slope is -1 for x is less than 0. And the formula for the slope for the second part is 2x minus 1. You're welcome to practice that using limits, but I'm just going to tell you the answer. So if a function is piecewise, then its slope formula is piecewise. So think about that. For x is less than 0, look at this slope. Always -1. There's no formula for the slope. It just is -1. But then the formula for the slope for anything greater than or equal to 0 is going to be determined by this function right here. So what is f prime at 0? F prime at 0 is 2 times 0 minus 1, which is -1. So sure enough, the slope is -1 on the parabola piece also. So since the slope is -1 coming in, and then slope is -1 going out, what they call the left hand and the right hand derivatives match. So it's also differentiable. So we haven't learned how to do trig derivatives yet, but sometimes if you're thinking, how do you expect us to do that? We can't do that yet. All you have to do is graph it. And it doesn't actually matter if the derivatives connect, if it's not even continuous. You always should check for continuity first. So this is mostly just an exercise in graphing sine and cosine. So sine starts at 0, goes up to 1, and comes back down. Although we're not going to graph it that far, we're going to stop right there because it's only going to 3/4. Cosine normally starts at 1 and then goes down to pi halves and then down to pi, and then it comes back up. So I'm going to use a dotted line in the beginning because I actually don't really want this part of the graph. And then right there, now I can switch to solid because 3/4 to the end. So solid, and then it's going to be going like that. So they don't even connect. So since it's not continuous, I'm just going to abbreviate that, continuous, it is not differentiable. So remember, I'm just going to say it again. Differentiable means the left-hand derivative and the right-hand derivative match, like this one, the -1 and the -1. But before you can even figure out the limits, if it doesn't connect, it doesn't matter. And this is a particularly interesting one because their slopes do match. So kids that don't graph it would say, oh, this slope is -1 when we learn how to do that. And this slope is also -1. So a kid that doesn't graph it is going to say, oh, the two slopes match. They're both -1. But it doesn't matter because it's not continuous. Last one, we're almost there. The graph of y is equal to the absolute value of x has a tangent line at 0. So this is something that's a little tricky for kids at first, and that is that in order for there to be a derivative, the left-hand limit and the right-hand limit have to match for the derivative. So you guys can see that this slope along here is -1. And then all of a sudden, it switches to +1. So because the left-hand limit and the right-hand limit of the derivative don't match, it is not differentiable. It's continuous, but it is not differentiable at 0. You might be saying, oh, but there's definitely a tangent line there. I mean, if you just wanted to just barely touch the curve, you could do it, and it has a tangent line. But unfortunately, that's not the definition of a derivative. The definition of a derivative is that if you have a smooth, continuous curve, so when you get to that horizontal tangent, it has gradually become zero. It was steep, and it got a little less steep, until it was zero, and then it starts to be a little negative. So it's a very gradual thing. It's not pointy. The main thing that kids end up learning in the end, more than just left hand and right hand derivatives, is it's never going to be differentiable at a corner, which is like that, at a cusp, which is like that. Okay. And of course, at a jump. Remember jump discontinuity? So even if it comes down and then it continues in the exact same slope, doesn't matter. So what I'm going to do is I'm going to keep giving you guys little bits of theory along the way. So this was kind of your theory part, these last 3 questions where we talked about differentiability. Notice we did not spend the whole time on it. It's not ever going to be my goal to do that. Mainly, you have problems that you need to be able to physically do, and that's what you'll be tested on. But for right now, I'm not really going to test you so much on the theory. I'm just going to keep talking about it every single class until by the end of the year, you hopefully understand the theory, in addition to being able to do the mechanics of the problems. Okay, this lesson ends the first unit, which was very short. The next unit is going to be very long. There's only 5 units for the entire year, but you are not 1/5 of the way through the year. So this is the end. We are probably in some kind of half virtual instruction. I don't even know I'm making this video in August, but we'll figure that out when we get there. But the point is that this is the end of this unit. So have a great day.